Hello everyone. In today's video, we're going to be covering the single responsibility principle, which is the first part of the solid design principles, and in my opinion, one of the most important principles you need to understand in order to develop clean and well understood code. So let's get started now. Before we get started, I want to talk about today's video sponsor, which is Atlantic.net Hosting, and this is an incredible host. Jump into the video you came here for. Welcome back to Web Dev Simplified. My name's Kyle, and my job is to simplify the web for you so you can start building your dream project sooner. So if that sounds interesting, make sure you subscribe to the channel for more videos just like this one. Now to get started, we have some code on the left-hand side here for a calorie tracker, and essentially all you do is you input the maximum amount of calories you want for a given day. It has a function which is going to track your calories by adding on the calories you pass to it to your current calorie count, and if at any point you exceed your maximum calories that you passed in, it's going to log out a message that just says your max calories are exceeded. So as you can see, we set it to a maximum value of 2,000. We logged out, we added 500, we added 1,000, then we added 700. So of course that's going to be over our maximum of 2,000, and we get our error message saying that we exceeded our maximum calories. And this code, it works fine, it's pretty small, it looks good, it doesn't seem like there's anything wrong with it, but it violates the single responsibility principle. And the idea of the single responsibility principle is that all of your classes, modules, functions, anything inside of your code that can be put into a single part, for example, this calorie tracker class, it should have one single responsibility. And that means it should only ever have one reason to change. But our calorie tracker has two reasons it would ever change. The first reason, and the obvious reason, is if we change the code for how we track our calories or how we calculate the calories that we're tracking, that is going to be needed to change inside of this class and inside this function here. But if we want to change how we notify the user when they go over, right now all we're doing is logging to the console, but if we wanted to, for example, email the user instead, we would need to also change this class. That means that this has two reasons to change. Number one, if we change how we track our calories, and number two, if we change how we log our calories. So what we want to do is actually take the logging of our calories portion out of this class and move that into something else. And in JavaScript, we have modules that we can use, and generally, you're going to be using modules instead of classes, so we're going to move this logging into its own module that has one responsibility, which is logging. So let's create a new class for that. We'll just create a file which is going to be called logger.js, and inside of here we just want to make an export default function. We just want to say log message, and this is going to take in a message, and then all we want to do is log out that message. And now we have a simple logger class, which encapsulates all of the logic of logging our calorie surplus. And we can actually just import that. So we can say import log message from logger.js. Make sure we put the dot slash at the beginning, there we go. And now we can just call that down here. We can say log message, and we just want to pass it in. In the message we are logging inside this function. Now if we save it, you can see everything over here is working exactly the same, and we can even change this, and we can just say max calories exceeded, add a little bit of stuff at the end, just so you know that this executed. And now we're following the single responsibility principle. As you can see, calorie tracker has one reason to change. The only reason we change is if we change how we're tracking our calories, whether it's how we're adding to the current calories or checking the max calories. If any of that logic changes, we change our calorie tracker. Then we have this logger here, and the only reason we ever change this logger is if we change how we're logging. For example, instead of doing a console log, we could just email the user instead. And this would change inside of our logging class here, this logging module. And now, each one of our sections of code has one single reason to change. And this is great. It makes your code so much easier to follow and to read. And this is something that a lot of people, especially people just learning programming, or even intermediate developers, always mess up on. I know I'm super guilty of making the mistake of cramming so many things into one class, one file, one module, one function, and it just becomes huge. It does so many different things, and in reality, I need to break these apart into smaller functions that all do individual things. That way, when I need to change something, I only have to change one thing. For example, if I want to change the calorie tracker, I do it in one single place. If I want to change the logger, I do it in one single place. I don't have to worry about going and changing something every time I need to make a change to something else. It shouldn't have to be affected if it's not directly related to the change. For example, how I tell the user about going over their calorie surplus has nothing to do with how I track calories, so I need to separate those from each other. And that's all there is to the single responsibility principle. If you like this video, make sure to check out my other videos linked over here, and let me know if you want me to cover the other letters of the solid design principles in future videos. Thank you very much for watching, and have a good day. Hello everybody. Thank you so much for all the incredible support that you gave me on the single responsibility principle video. It really encouraged me and made me want to get the second solid principle out as quickly as I could. So in today's video, we're going to be covering the open-closed principle, which is the O portion of the solid design principles, and in my opinion, one of, if not the hardest of the solid design principles to understand just by reading the definition. But in this video, I'm going to give you the perfect example, which is going to make the open-closed principle incredibly easy to understand. So let's get started now. Welcome back to Web Dev Simplified. My name's Kyle, and my job is to simplify the web for you. So if that sounds interesting, make sure you subscribe to my channel for more videos just like this one. Now to get started, I'm going to read you the Wikipedia definition of the open-closed principle, which is that software entities, classes, modules, functions, etc. should be open for extension, but closed for modification. And if you're like me, that definition sucks and doesn't explain at all what the open-closed principle does. It's saying that something needs to be open and closed at the same time. It's really confusing in my opinion, so instead, I figured it's best to just start with a code example to show you the open-closed principle in action by starting with an example that does not use the open-closed principle. As we have over here, here we have a function called print quiz, which takes an array array of questions. It loops through each one of those questions, and each one of those questions has a description, which it prints out, which is over here is going to be our name. If we just save this, you can see this video is useful. What is your favorite language? It's essentially the question. And then it checks the type, and depending on what type the question is, it prints out different options inside of here. And as you can see down here, we have our different questions with our different types as well as their options, and then we're calling print quiz at the very bottom. see, it's this video is useful, what is your favorite language? It's essentially the question, and then it checks the type, and depending on what type the question is, it prints out different options inside of here. And as you can see down here, we have our different questions with our different types as well as their options, and then we're calling print quiz at the very bottom. And if you're unfamiliar with a switch statement, which we have here, it's essentially just like a big if statement where it's saying if the question type is Boolean, then do everything in here. If the question type is multiple choice, then do everything in here. And if it's text, do everything in here. You don't really need to know what a switch statement is, but many times when you see a switch statement, it's actually because there is a violation to the open-closed principle. And as you can see, this code actually works just fine. It prints out our quiz perfectly fine, exactly how we want it to be printed. But what happens if later on we want to add a new option or a new question type to our quiz that we want to print out? We don't want just Booleans and multiple choice and text. We want to add in the ability for users to be able to check for values across a range. Well, the first thing that we need to do is actually add that new question. So we can just come in here and we can say that the type is going to be range, for example, and this is going to have a minimum and a maximum value that it allows you to input.
I forgot the comma, of course. Actually, you don't write a comma here until you actually put something in, so I didn't forget. Yeah, range, and then description.
Input, and for the description, we can just say something like, what is the speed limit in your city? There we go. And now if we save that, you can see it's printing out the description, but obviously no options are being printed. And that's because we have to change this giant case statement. We need to add another case, and this new case is going to be for the type of range. And we want to just print out here, minimum and maximum. Now if we save that, you can see over here, we have our minimum and maximum being printed out for that question, and our new range value was properly added, and our ability to print the quiz now works again. But we violated the open-closed principle, and that's because of this print quiz button. What happens is when we change something out here, we're changing our type. We're adding a new type of question. We have to actually go into our print quiz and change it. This is the part where it's saying that this should be closed. We don't want it to be open. So we need to have this closed off where we can't make changes to it. So if we're changing the code outside, we should never change the code inside. This print quiz should just automatically work if we add a new quiz type without us having to come in here and change it. That's what the closed portion of the open-closed principle is all about. The open portion is essentially saying that we have the ability to add new things. So we have the ability to add a new range type, for example, without having to make any changes. We can come out here, make a new type of range, and this print quiz is just going to automatically know what to do with that range type that we just created. So the open portion says that we have the ability to create new types of things and allow those things to work automatically without having to make changes, which is the closed portion of the open-closed principle. And it may seem really difficult, like how in the world are we going to make it so this automatically works? We have to put this code in somewhere. And that's where the idea of breaking this print quiz out into smaller individual components where print quiz doesn't actually need to know about the internals. As you can see here, we have the switch statement with this type variable. A lot of times when you have a switch statement or you have a bunch of if statements like if this or if this or if this or if this, almost always it's a violation of the open-closed principle. What we need to do instead is break this out into individual classes. So we want a Boolean class, we want a multiple choice class, a text class, a range class, and those classes are going to handle the printing inside of them. And then inside of our print quiz function, what we do is we just call that print function. And then when we add a new type, we just make a new class and we make that type know how to print itself. And this print quiz is just going to work just as before. So let me swap over to what that's going to look like. So I just finished swapping over all of the code to be using the open-closed principle. And as you can see, we now have classes. We have a Boolean question, which prints out our Booleans. We have a multiple choice question for printing out multiple choice. Same with text, same with range. And now the really brilliant part is our print quiz function is so small now. All it does is print out our question choice, which is a function each one of our classes has. Then our list of questions is just new versions of those classes. It's super simple and super straightforward. Essentially, what we've done is we've broken out this massive switch statement of logic into individual classes that know exactly what to do with their type. Even multiple choice here, you can see it takes an extra parameter for options, and then it prints those out just like it needs to. And the reason this is so much better is that when we, for example, make that new range type, let's remove this for now, and let's say, okay, we want to make a new range question. All we do is say new range question, and as you remember, this is just what is the speed limit in your city, just like that. And now we can just create that class. So we're going to have range question as our class. It's going to have a simple constructor, which takes in, a description. And inside of here, we're just going to set the description for that class. So we'll say description is equal to description. And then we just make sure we call print question choices. So we'll copy that down. And this just says minimum and of course maximum. If I can spell properly. Just like that. And there we go. We never had to touch print quiz. This was closed. We never had to touch it, but it was open to be extended because we were able to make this new range question class, which made our print question or our print quiz actually do more things. It extended it. It was able to do more things by printing out this range question, but we never had to open it up and actually make changes. It was closed to changes and open for extensibility. And that really helps kind of solidify that confusing definition where things can be open and closed at the same time. Essentially, it allows you to make modifications to the code without actually modifying the code that is being extended. Really, the open-close principle at its root is saying that what you want to do is instead of changing code, you want to create new code. And that new code is going to work with your old code in order to do things like printing out these new types of questions. Now, it's something that, in my opinion, you shouldn't always follow. I think it's great to follow it when you can, but taking it to the extreme of never modifying your code and always making new code is just a little bit too much in my opinion. But when you see those big switch statements, those big if statements, always realize that you're almost always violating the open-close principle, and you should refactor that code to use, for example, classes or functions or modules, something that breaks out that logic into individual classes or functions that have the logic in them, and then that crazy switch statement can be broken down into one single function call. And this code right here is so much easier to follow because I promise you, this old code that we have here, you know how easy it is to forget to add in this new case for the range when you create the range question? I know it's really, really easy to do because I've written code that looks like this before, made some changes, added some new things, and I forgot to add the case statement here to actually properly handle it, and my code was broken. I didn't realize it. But with this system, you can't forget. You have to create the class, and in that class, you're always going to put the print question. Everything just lives in the same spot. It's almost impossible to mess up. While this system, like I said, it's so easy to make mistakes. I do it all the time when I write code like this. So almost always try to avoid these big confusing switch statements and use the open-close principle to write this much cleaner and easier to maintain code. And that's all there is to the open-close principle. It's much easier than it first sounds. So if you enjoyed this video, make sure to check out my other clean code related videos linked over here and subscribe to my channel for more videos just like this one. Thank you very much for watching and have a good day. Hello everyone. You have really been loving my solid design principle videos. So here's the third one, which is going to be covering the Liskov principle, which in my opinion is one of the most important principles for writing really good object-oriented code. So let's get started with that right now. Welcome back to Web Dev Simplified. My name's Kyle, and my job is to simplify the web for you so you can start building your dream projects sooner. So if that sounds interesting, make sure you subscribe to the channel for more videos just like this one. And now to get started with the Liskov principle, I'm first going to read off the definition, which is that if S is a subtype of T, then objects of type T may be replaced with objects of type S. And that is a mouthful of jargon that really doesn't make too much sense. But essentially what this is saying is if you have an object, a class, let's say for example you have a class of animal, every single place that you use the animal class, you should be able to replace it with one of its subclasses. So if you have another class called dog, which inherits from animal, then every single place that you use animal, you should be able to use dog, and it's going to work just as well as it did before. That is what the Liskov principle says. Anywhere that you use one type of class, you need to be able to use all of the subclasses of that class, and it should work just fine. So let's jump into an example where we have two different classes. We have a rectangle class, and then we also have a square, which extends rectangle. And that is because we know that every single square is going to be a rectangle, because every square is a four-sided object, and a rectangle is also a four-sided object, so we know every square is a rectangle, but not every rectangle is a square. So that's why we have the relation in this direction, where a square extends rectangle. And all this is it takes a constructor, which gives you the width and height, and then there's a function for setting the width, setting the height, and then getting the area. And then inside of the square, we changed our set width and set height. We actually don't even need this area. We changed our set width and set height so that it's always going to set both of the sides, the width and the height, to always be exactly the same, so that it's actually a square and not a rectangle, hence why it's in the square class. And then we created two rectangles down here, we increased their width and then printed them out. And this increase width function, all it does is it sets the width of the rectangle to one more than what the width currently is. And as you can see, we have two rectangles. This one right here is 10 by 20, this one's 5 by 5. And so when we increase the width from 10 to 11, we get an area of 22, which we see printed on the right. And here, when we increase the width from 5 to 6, we get an area of 30, which is shown over here. But you may notice that this rectangle right here is actually a square. So we should just change this to be a square, change rectangle 2 to just be square, and we can come and replace all of our rectangle 2's with square, and we should see the exact same thing happen. Everything is going to be the same over here, right? 22 and 30, because we're now calling this increased rectangle width with a square, which is a subclass of rectangle. So according to Liskov's principle, all of this should work exactly the same as before. But when we run this, you'll notice we get 36 here as the area of our square. And that is because when our square enters this increase width function, it increases the width by 1, but that also increases the height by 1, because our width and height always are exactly the same. So now it is a 6 by 6 square instead of a 6 by 5 rectangle. So this function right here is breaking the Liskov substitution principle. Essentially, the problem is that our subclass of square is not actually compatible with every function that we're using a rectangle for. Our square cannot be substituted in place of a rectangle, so we now are failing that Liskov substitution principle. And this is sometimes a tricky problem to fix. But in this example, one of the easiest ways to fix this would be to change what we're inheriting from. So we want to create another class. This class would be, for example, shape. And this shape class here would actually just have this area function, for example. So we could have an area function, and it'll be implemented, and it'll do some kind of code in here to return the area. And then our rectangle is going to extend shape, and our square is going to extend shape. So now our rectangle and our square are both extending from shape instead of extending from rectangle. And now our API is going to work just fine, because when we set the width, for example, in our rectangle, it's going to modify just rectangle stuff. And we would need to have, for example, increase shape width. But obviously our shape doesn't really have a width, so this doesn't really work as is. But you get the point that what we need to do is we need to create an object that we can actually inherit the rest of our objects from. This example is more so just to show you how the Liskov principle works, and how code that may look fine, this rectangle and square code we had before, is actually incorrect because it's violating that Liskov substitution principle. I have another example that I'm going to jump to where we can show exactly another way that the Liskov substitution principle is violated and how we can actually fix it. So here I have another example of the Liskov substitution principle, and we have three different classes. Our first class is our base class, which is a bird. And all of our birds can fly because birds can fly, so we have a fly function on our bird. Our next class is a duck class, which extends bird because it is a bird, and it has a quack function because ducks quack. And then lastly, we have a penguin function, or a penguin class, which extends bird because a penguin is a bird. And penguins can't fly. So we're throwing an error saying, hey, we can't fly, we can't actually do this. But we also have a swim function because penguins can swim, so it says I can swim. And then inside of here, we have a make bird fly function, which just calls fly on a bird. And then we're creating two different birds, duck and penguin, and then we're making them fly. And as you can see, the duck prints out I can fly just fine, but the penguin is throwing an error saying it cannot fly. And this is again another instance of the Liskov substitution principle not working. Because this is a bird function, so it expects a bird class. And we're passing in both of the subclasses of bird, duck and penguin. And according to the principle, every subclass of a class must be able to make this function work properly. And the duck function works fine. So this duck is passing the Liskov substitution principle. But the penguin class is not, because the penguin class cannot fly, and thus it works differently than its parent class, which can fly. So we're failing the Liskov substitution principle. And an easy way to fix this is to change it so that we don't just have a bird
What the hell?
subclass, we have a flying bird subclass. So we're going to say we're going to have flying birds, and our duck is going to extend from flying bird, and then we're also going to create a swimming bird. And then we're going to put our swim method inside of there. So let's just copy that, paste that into our swimming bird, and of course, since our penguin can swim, it is going to be a swimming bird, and we don't need to worry about this fly function anymore. Now what we can do is we can make a flying bird fly, and we can have another function which is going to make a swimming, make swimming bird swim, and then we're just going to call swim here. So now we can say make flying bird fly on our duck, and we can make a swimming bird swim on our penguin, and you can see that works. I can fly and I can swim. And this code right here is passing the Liskov substitution principle, because every subclass of swimming bird is able to properly call this function, and every subclass of flying bird, in our case duck, is able to properly call the make flying bird fly function, and everything is working as if it was the parent class. The code doesn't know that you have a subclass, and because of that, it needs to work as if it was the parent class. But this code has a problem. And this is a problem I don't really want to get to in too much depth in this video, but it is a major problem with object-oriented programming and inheritance in general. And that's that a duck can also swim. So a duck can fly and a duck can swim, but we can't inherit from two different classes. You can't inherit from flying bird and from swimming bird. You can only inherit from one of them. So what we need to do is maybe create a third class, which is flying swimming bird or something like that. And that really doesn't work very well, as you get lots and lots of different permutations of flying, swimming, and other types of birds. So what a lot of times you're going to hear about is composition, which is the idea of adding in functionality instead of inheriting functionality. So we would add the swimming functionality to our duck and add the flying functionality to our duck without ever extending any base classes. And if composition is something that you want to hear more about, make sure to let me know down in the comments below, and I'll make an entire video of composition versus inheritance and why composition is so much better than inheritance. But for the purposes of this video, it's just important to know that as you start following the Liskov substitution principle, you may run into issues like this where you have really complex inheritance trees. And if you run into that problem, you need to look at composition as a way to solve that, because inheritance, when you get into situations like this, can become incredibly messy and is not the best way to write your code. But for most instances, inheritance is going to work just fine, and it's not going to be as complex as this, for example. All you need to know, though, for the Liskov substitution principle is that if you have a function that accepts a class, every single subclass of that class must also be able to enter that function and work properly. That's all there is to the Liskov substitution principle. So while the definition is really confusing, it's an actually very simple principle to follow. And that's all there is to the Liskov substitution principle. If you enjoyed this video, make sure to check out my other videos linked over here, and subscribe to my channel for more videos just like this one. Thank you very much for watching, and have a good day. Hello everyone. In today's video, we're going to be talking about integration segregation with JavaScript, which is the fourth solid design principle and one of the easiest in my opinion to understand. So let's get started now. But before we get started, I want to talk about how you can get an entire year of hosting for free with a powerful server, and that's by using Atlantic.net, which is the video sponsor for today's video. And if you use the code Kyle when you check this for free for an entire year, that is amazing. This server also has incredible redundancy and incredible security, so you don't have to worry about problems with your data going missing. It's always going to be there for you. So make sure you use the code Kyle when you sign up and use the link in the description down below. Welcome back to Web Dev Simplified. My name's Kyle, and my job is to simplify the web for you, so if that sounds interesting, make sure you subscribe for more videos just like this. Now, in JavaScript, there's no such thing as an interface, and the entire idea of the interface segregation principle is about segregating your interfaces and making them smaller. So I'm going to show you an example of what this would look like without JavaScript, and then I'm going to show you how you can use the interface segregation principle in JavaScript because it's actually applicable even without interfaces. So in a normal language with interfaces, you'll define an interface and every single thing such as all the properties and all of the different methods of that interface. And then every single class that implements that interface needs to define all of the methods in that interface. But the problem is that when you have large interfaces like this, which do lots of different things, for example, this has a name, it handles attacking things, it handles moving, it handles taking damage and health, for example, in a video game, and you may have a character here which implements all of those. It needs to be able to move, attack, it has health, it takes damage, it has a name, everything makes sense. But a turret, for example, it can't actually move, so having this move functionality on it really doesn't make sense. And with the interface segregation principle, it's saying that whenever you have an interface, you need everything that implements that interface to use every single portion of the interface. And right now, a turret which is implementing this interface doesn't use movement, so we don't actually use all of the different parts of this interface. So we're breaking the interface segregation principle. And now in JavaScript, a very similar way of doing this is using classes and inheritance instead of using interfaces. So if we just remove this code and come down here, I have almost the exact same example. As you can see here, we have an entity, but instead now it's a class instead of an interface, and it has all those same properties, name, attack, damage, health, and it has these functions, move, attack, and take damage. And these are just printing out to the console so we can see that everything works. Then we have our character class, which is just extending entity, and it's not doing anything else. It's just doing the stuff in the entity class. We then have a wall, which can't move and it can't attack. So it has 0 for attack damage, and we're just returning null for move and attack. And then a turret can't move or take damage, so we're returning null for those. And then down here, we're just initializing our turret, character, and wall. And if we save this, you can see our turret is able to attack our character is able to lose health, it's able to move, and the character is able to attack the wall because the wall has health. And this looks like it works. I mean, obviously the code works, but the problem is we have this base class, this entity, which has all these different functionalities and all these different properties. But for example, a wall doesn't use all of them, and our turret doesn't use all of them. And this is the same problem with interface segregation, where we noticed we had a big interface that had a lot of properties, a lot of methods, and not everything was able to use all of them. This is the same exact problem, and we need to implement the same style of solution, which is to break apart our interface. But in our case, this is a class. We want to break this class into individual components for movement, for attacking, for taking damage. I actually have an entire video on composition versus inheritance, which I'm going to link in the cards and the description for you, but I'm going to show you how to do it in this instance, how we can break apart this big entity class into much smaller components that we can add to individual classes as we need. So here we have the actual final example of what we would do if we moved to components, which are essentially like smaller interfaces. We just broke apart our class. And as you can see, our entity class is now really small. All it is a constructor that takes in a single name. And then below that, we have our different components. These are our smaller interfaces in that interface segregation model. And as you can see, our mover component, all it can do is move. And this function, this console.log this.name, this is the exact same as our move function here. We just moved that over into the move function in this mover component. We also did the exact same thing with the attacker. We just put the attack functionality in there, and this handles attack damage, the name, all of that information. And the same thing for has health. This allows our unit to take damage, and it also modifies the health variable as needed. And then as you can see down here in our character class, we're extending our entity, which as we know just has that name portion of it. So we're pushing the name up to that entity, but we're also taking in the extra parameters of damage and health and setting those inside of our character. And now, in order to make our character actually work with these components, what we do is we take the prototype of our character, which is essentially the definition of our class, and we're adding in the functionality of mover by saying object.assign the prototype, and we're adding in the mover to it. We're also adding an attacker in, and we're adding the has health into this. Similar thing for the wall here, except for the wall can't attack or move, so we're only adding the has health portion. And the same thing with the turret, it can't move and it can't be destroyed, it has no health, so we're only adding the attacker portion to it. And if we save, you can see over here, we get the exact same output with the same exact code down here. Our actual code that we're using to create these objects and actually interact with them is exactly the same between this example and our previous example, as you can see here. But the difference is that in this example, for example, our turret.move doesn't actually work. You see we get an error. There is no move function on our turret. But if we were to switch over and use our previous example, so if I change this to be our previous example, we're now running our code here, and I call turret.move, you can see that it's not actually doing anything, and that's because it's entering inside here. I can just say, for example, error, and as you can see, we're getting error printed out because turret can't actually move, but we can still call the move function, which is why you want to break out your interfaces or large classes into smaller components or smaller interfaces so you don't have this problem where the turret is extending all of this information for moving even though there's no way that the turret can actually move. Instead, you want to use these small components, as you can see here, where we just assign these components to our different classes so that now our turret can't actually move. We can try to make it move all we want, but every single time we're just going to get an error if we switch over to that script. As you can see here, we're getting an error because the turret cannot move. Same thing if we tried to get the wall to move, we're going to get the exact same error. This makes it so that each of our objects and each of our classes only ever implements the information that it can actually use, and it doesn't implement anything else that it cannot use. That is really crucial and the main point to the interface segregation principle. And that's all there is to the interface segregation principle. If you're interested in checking out other solid design principles, I have them all linked over here for you to check out. And if you enjoyed this video, make sure to subscribe to the channel for more videos just like this one. Thank you very much for watching and have a good day. Hello everyone. In today's video, we're going to be covering dependency inversion, which is a fairly abstract concept to think about. So in this video, I'm going to simplify it and give you concrete examples of dependency inversion so you will understand it in depth by the end of this video. Let's get started now. Welcome back to Web Dev Simplified. My name's Kyle, and my job is to simplify the web for you so you can start building your dream projects sooner. So if that sounds interesting, make sure you subscribe to the channel for more videos just like this one. Now to get started, I want to talk about the abstract concept of what the dependency inversion principle is by using a concrete example. And right now we have an application that allows users to buy different things from our store. So we have some form of store over here on the left-hand side, which is calling out to the Stripe API in order to handle all of the credit card information and user payment processing. So what this is saying is our store depends on the Stripe API. And inside of our code, we have exact lines that say like stripe.makepayment or stripe.checkcreditcard inside of our store code. So our store is very coupled to our Stripe API. It calls it directly. And this is a little bit of a problem because what happens if we want to test our code very easily? We have to make all of these calls to the Stripe API, and we don't want to call the Stripe API while we're testing. Also, what if we want to switch to PayPal or allow them to pay with PayPal on top of Stripe? Adding that in means we have to change tons and tons of code in our store, swap out all that Stripe code, and put in all of this PayPal code. So what happens in the dependency inversion principle is that you add in a piece in the middle, kind of an interface, which contains all of the behavior that we want our API to be able to do. So we implement this payment processor. And now our store calls the payment processor and says payment processor.check credit card or payment processor.make payment, whatever it is. And this payment processor doesn't depend on anything. It's just an API. It's just a bunch of functions that we can call, like check credit card, do this, do that, make payment. It doesn't matter what it is, but it's just an idea of what we can do. And then we have a specific implementation. So we have our Stripe implementation of our payment processor. And now we can just plug our Stripe implementation into our store. We give our store the Stripe implementation, and it'll call methods on the payment processor. But those payment processor methods will actually be calling this Stripe API, since it's set up to delegate those methods to Stripe, and that Stripe interface that we created is allowing it to talk with Stripe. So what this allows us to do is to actually have two different APIs. We can create a payment processor for PayPal and a payment processor for Stripe, and they both use the same exact API, the same exact underlying functions. So our store never has to change unless we change our payment processor, which is just an abstract idea of the different types of payments that we can make. The idea of this is a lot of times referred to as like the adapter pattern or the facade pattern, where you create this wrapper essentially around external dependencies that you have. So that way your code depends on the wrapper you created and not the actual implementation of the detail for the dependency you're using. And that's the idea of dependency inversion. You do not want your high-level code, for example, this store class, this store method, whatever it is, to depend upon the low-level implementation of your dependencies. We don't want it to depend on how Stripe works or how PayPal works. We don't depend on this payment processor that wraps those functionalities, which is something that we can control and easily make Stripe and PayPal look exactly the same to our application. So if we change out Stripe, we change out PayPal, Stripe updates, PayPal updates, it doesn't matter. Nothing in our code will change inside of this store. It will remain exactly the same. So now that I've talked about what these different ideas are, let's go into a concrete code example. So here's a concrete version of that example where we have our store, we have Stripe, we have PayPal, which we'll look at a little later, and then some implementation details actually calling that store. So let's take a look at this code in depth. We have our store, which is going to take in a user. It's going to create that new Stripe object. And this Stripe class that I'm referring to here is, you can imagine, like the actual Stripe API. I obviously don't want to use the actual Stripe API in this example. So this Stripe class here is essentially our version of the Stripe API. So just think of this as the Stripe API for these examples, and it'll make a lot of sense. So we're creating an object that allows us to access the Stripe API directly. Then we can purchase a bike and a helmet inside of this store, and we're just calling the Stripe API, making a payment, and a bike cost $200, so we're saying 200 times the price of the bike. And since Stripe always wants us to send the amount in pennies, we multiply that by 100, so then we're sending them the amount of pennies it cost to buy this bike. Same thing for helmet, except for a helmet is only $15 instead of $200. Now if we go to our Stripe class, you can see it takes in a user, which is the user we're going to make payments on, and then it's going to make that payment using the amount in pennies, like I said, and it just logs out that the user paid the amount of money they paid in dollars using Stripe. And we created a new store down here where John is going to buy 2 bikes and 2 helmets. And if we save this, you can see that since our bike cost 200 and he bought 2, John made a payment of $400 with Stripe. And then since the helmets are $15 and he bought 2, he's now made a payment of $30 with Stripe. So now let's say this is working great, everything's going well, but Stripe changes their pricing, and now Stripe is really expensive to use, so we want to switch over to PayPal, because PayPal is really cheap, it's way better for our business, so we're going to use PayPal. So now here's what the PayPal API looks like. It doesn't take in a user in the constructor, it actually takes a user in the make payment method, and it wants its amount in dollars. It doesn't take it in pennies, it takes it in dollars. And then it of course logs out the exact same thing, except for it's saying that it bought it with PayPal. So in order to use PayPal inside of our application, the first thing we need to do is to change our constructor. We have to change this to say this dot PayPal is going to equal to a new PayPal. And since PayPal doesn't take the user object, we can't send it. So we have to also create a user variable here. So this dot user equals new or equals user, just like that. Let's comment out our Stripe. And then in order to make a payment with PayPal, what we need to do is say this.paypal.makePayment. We want to do the price times the quantity. And we need to also make sure we pass in this.user. And we need to do the same thing here with the helmet. So we can say this.paypal.makePayment, this.user, the price times the quantity. And now, if we save our code, you'll see that it's exactly the same. John made the $400 payment with PayPal, and he made the $30 payment with PayPal. And that was fairly painless to change over, but you can imagine in a real application with a real store, the amount of times that you have payment code is going to be a lot. It's going to be all over the place. And also, the number of methods inside those APIs is going to be a lot more than one, and there's probably going to be a lot more differences. Luckily, we have two methods that both are called makePayment, which allow us to easily transfer between these two different APIs. But you can imagine the way PayPal does payments and the way Stripe does payments are going to be very different. So making a transition like this is going to be really hard in most cases. So what you want to do instead is to create some kind of intermediate API. This is going to be your wrapper, which is going to wrap around Stripe and wrap around PayPal. And the idea of this wrapper is that it has the exact same functions, the exact same methods, the exact same interface. So in our store, we never have to change our store. So let's imagine that we have a class called payment processor, and this is just going to take in a user. So we can say here payment processor, just like that. And then our payment processor is just going to have a function called pay. And this function that's called pay is just going to take in the amount in dollars. So we'll say 200 times quantity. And we'll do the exact same thing down here, except for we want to just pass in 15 times our quantity. And we want to make sure this is the payment processor. Whoops. Payment processor dot pay. So there we go. Now we have our code using this payment processor, which always takes in a user in the constructor, and it's always going to take in the amount in dollars for a function called pay. And we want to have different payment processors, one for Stripe and one for PayPal, which wrap these dependencies of PayPal and Stripe so that we don't depend on the exact implementation of Stripe or PayPal. So let's create one first for Stripe. We're going to call this our Stripe payment processor. Whoops. And our Stripe payment processor, just like we mentioned earlier, is going to take in a user, and it's going to set the user equal to user, because this needs to match the API we created up here. It's also going to have a function called pay, which is the amount in dollars. And all we want to do is call Stripe. So up inside of our constructor, we can actually just say this.stripe is going to be equal to a new Stripe. We can pass in that user, and we don't even need to save this user anymore. And down in here, we can say Stripe.makePayment, and we want to make sure that we make this payment in cents. So we can say amount in dollars divided by, multiplied by 100. So now that we actually have this payment processor created, what we can do is pass this payment processor into the store. So instead of passing a user in here, we're going to pass in our payment processor, and we don't need to create a new payment processor in the store anymore. We can just set that to our payment processor. Now down inside of our store, all we need to do is pass in our new Stripe payment processor with the name of our user, for example, John. And now if we save, you see that this payment processor that we created for Stripe is passing off all of our function calls to the Stripe API down here, and you can see it's printing out the proper information on the right-hand side of the screen. And the best part is we can create another payment processor, if we just copy this, for PayPal, and all we have to do is change this single line down here where we instantiate a PayPal processor instead of a Stripe processor. So let's create that PayPal processor, just like this. And we want to first set our user. So we're going to set it to the user we got passed in. And now inside of this pay function, we want to make sure that we call that PayPal API. So we'll create the PayPal API up here, just like that. And it doesn't take in a user, as you remember. So now we can say this.paypal.makePayment, and we want the amount to be in dollars, and we want to pass in the user, just like that. And now, if we save and come down here and change this to our PayPal processor, you'll see that we're getting an error, and that's just because we need to make sure we use this.user inside of our make payment function. And now when we save, you see John is able to make that payment through PayPal and this other payment through PayPal, and we didn't have to change any of the code inside of our store. This all stayed exactly the same because we have this payment processor interface or method or abstraction, whatever you want to call it, that is allowing us to not have to change any of this code, and all we need to do is create a new payment processor, wrapping the API we want to use, and then we just pass that into the store down here. This setup is very similar to the facade pattern or the adapter pattern, which I have videos on the facade pattern you can check out. I'll link in the cards and the description down below. And that's all you need to know about the dependency inversion principle. If you enjoyed this video, make sure to check out my other solid design principle videos linked over here, and subscribe to the channel for more videos just like this one. Thank you very much for watching, and have a good day.
Alright. Was something? Web archive. Wayback Machine. Funny guys. That's pretty funny. I wanna be right back, mate. Shiba! Guess who's back? That's right, that's me, mate. That's me. Yeah, anyway, I got here. Uh, okay. I needed some epic music. Here you go. That's why I'm gonna wait you just come over to Wait, what? Loosely coupled subjects, okay. Reduction of coupling, yeah.
how unrecognized high IQ looks in kids. Constant overthinking. High IQ minds analyze everything. Bored.
Today, we are going to talk about composition over inheritance. Inheritance is when you design your type. Around what they are, while composition is when you design your types around what they do. We're going to learn about the limitations of inheritance and how to solve them using composition. This is a weekly show where we try to become more confident and excited about programming by learning intriguing things that we didn't know before. A tip is that you will get more out of this video if you have watched the previous episode about factory functions. You can do so by clicking there. Let's talk about inheritance a bit. Let's say that we are designing a game and I need a dog. What? After a while, we realize that our software, like everything, needs cats. So we create a cat class. And because nature calls, we add poop to the cat and dog class. That's duplication, we can't have that. So we lift poop into a shared animal class. And well, now we have a lot of animals pooping everywhere, so we need a cleaning robot that can drive and clean. We also need a murder robot that can drive and kill all the cats and dogs that are pooping all over your nice Scandinavian white floors. Since drive is now duplicated between cleaning robot and murder robot, we create a robot parent class to put it in. A couple of months of development go by. Your dog, your murder robot, and friends have grown into a mature, stable system. You're feeling good about it at this point in the project. Without fail, the project manager will say this: our customers demand a murder robot dog. The murder robot dog can kill, drive, and bark, but it doesn't have a digestive system, so it cannot poop. And now we are screwed. We simply can't fit the murder robot dog nicely into this inheritance hierarchy. I mean, I guess that we could create a new parent object where you put all the functionality that is shared. So maybe a game object with a bark method like this. But this means that your objects will have a ton of functionality that they don't use. You end up with a sort of gorilla banana problem where you request a banana but you get a gorilla holding a banana and the entire jungle with it. So maybe instead of a parent object we can just duplicate the functionality like this. We give bark to murder robot dog in addition to the dog. That is not as bad, but our mothers still wouldn't approve. Thus, composition to the rescue. Again, inheritance is when you design your types around what they are, while composition is when you design your types around what they do. Using composition, we would do this instead. A dog is a pooper that is also a barker. A cat is a pooper that is also a meower. A cleaning robot is a driver and a cleaner. And a murder robot dog is simply a driver and a killer and a barker. Now I am going to show you how to do this in practice using JavaScript. We're going to do this using normal functions and normal object literals. Behold, these are the definitions of barker and driver. I will let you contemplate these two functions in solitude for a bit before I continue. The astute of you might have noted that these functions are like the factories from the previous video, but instead of creating their own state internally, they accept their state as a function parameter. This is so that they can share the same state. Have a look at what the actual murder robot dog factory looks like. First, it creates a state object. It assigns some default values to it, speed and position. It also assigns the name from the function argument. It then uses something that you might not have seen before, object assign. What object assign does is that it takes an object, in this case just a new empty object, and assigns the properties from the other objects into it. So in this case, it creates a barker, a driver, a killer, and then merges them all into the new object and returns that object. We have our murder robot dog. Easy as pie. Object.assign is a handy function built into ECMAScript 6, but all libraries underscore Lodash has it. It is also super simple, it does almost nothing, so if you're feeling frisky, you can just write one yourself. It's like 7 lines of code. In summary, we have looked at an example of an inheritance tree that broke down, and then we looked at how to restructure it using composition. And finally, we looked at how to actually compose objects using JavaScript. The question that is probably on your mind right now is, when do I use inheritance and when do I use composition? Well, the vast majority of developers would say that you should favor composition over inheritance. Me, personally, go one step further. I don't see the point of using inheritance at all. I don't think it's a good pattern, and I don't think it should be used. A lot of people are going to tell you that if something is a relationship, then it should use inheritance. For example, me, Matthias, is a man, so I can inherit from the man class. If the relationship is more of a has-a nature, such as a car which has an engine, then you should use composition. But I think that reasoning is topsy-turvy. While it is true that I am a man, I also have arms and I also have cooking skills. While it is correct that a car has an engine, it also is a vehicle. You can interpret pretty much any concept both ways. When it comes down to it, I think that the problem with inheritance is that it encourages you to go predicting the future. Inheritance encourages you to build this taxonomy of objects very early on in the project. And you are most likely going to make big design mistakes while doing that, because humans cannot predict the future, even though it feels like we can. And once you built yourself into that inheritance taxonomy, it's really hard to get out of it. I think it's just better to use composition from the start. It's more flexible, it's more powerful, and it's really easy to do. So why not? And that is it. That's my thoughts on composition. But what are yours? Comment down below, or maybe just hit like if you're not the talkative type. In this show, we try to become more confident and excited about programming by learning new intriguing things that we didn't know before. Built into ECMAScript 6, but to restructure. If you're feeling frisky, you can just write one yourself. It's like 7 lines of code. In summary, we have looked at Dash has it.
Hello everyone. To individual
The Master of Studies in Entrepreneurship provides entrepreneurs
Hello everyone. Where the rest of our objects from. This example, we're just going to call swim here. So now we can say make flying bird fly on our duck. Hello everyone. Have the actual final example. Of what we would do if we moved to components, which are essentially like smaller interfaces. We just broke apart our class. And as you can see, our entity class is now really small. All it is a constructor that takes in a single name. And then below that, we have our different components. These are our smaller interfaces in that interface segregation model. And as you can see, our mover component, all it can do is move. And this function, this console.log this.name, this is the exact same as our move function here. We just moved that over into the move function in this mover component. We also did the exact same thing with the attacker. We just put the attack functionality in there, and this handles attack damage, the name, all of that information. So we're pushing.
additional solid. So single thing, some open close with code that remember interface resolve dependency version. Solid. It's like with objects that are very like interdependent. If you change one, you affect the other kind of thing. In a way that you gotta change the other. Okay, but it's not as bad anyway.
Слушайте Яндекс.Музыку дома, на Яндекс.Станции, телефоне или компьютере бесплатно до весны.
Опять пищеварение? Фистал – это не только панкреатин для снятия симптомов, но и активный компонент, способствующий...
Today, we are going to talk about composition over
Then
inheritance.
you're gonna have like penguins that fly and shit.
Феликс, у меня для тебя новинка. Феликс – вкусный паштет. Посмотри, какой нежный.
Как здорово! Вы...
Hi there. There are what I would consider to be 7 deadly sins when it comes to programming. Things that will grind your code quality into dust if you don't heed their lessons. Now, I hope you've never had to hear someone tell you that you write bad code, but if you have, there's really nothing to be embarrassed about. We all write flawed code as we learn, and the good news is, it's fairly straightforward to make improvements if you're willing. In essence, that's why I've created this video, to guide you to becoming a better coder. So, let's look at the mistakes you might be making and see if we can fix them. The first thing I see people doing is not using programming standards. They give us rules to follow, like white spacing, file structure, and other philosophies that we apply to make our code consistent and therefore easily readable. It's also especially important when working with other people because it allows everyone to rely on shared expectations. If you don't keep standards, it's kind of like switching fonts all the time. We can read it, sure, but the subtle differences throw us off and slow us down a bit. As for choosing a standard, if you aren't given one by your team, then there's plenty to choose from in the wild. The second thing, programming design principles, are probably some of my favorite ways to improve. You can think of principles like a general guide into becoming a better programmer. They're the raw philosophies of code. Now, there's a lot of principles out there, too many to cover in this video, but I will quickly show 5 very important ones which go under the acronym of SOLID. The S in SOLID stands for single responsibility, and it teaches us that we should aim to break our code down into modules of one responsibility each. So, if we have a big class that is performing unrelated jobs, for example, we should split that up into separate classes to avoid violating the principle. It's more code, yeah, but we can now easily identify what the class is trying to do, test it more cleanly, and we can reuse parts of it elsewhere, without having to worry about irrelevant methods at the same time. This actually becomes more important as we progress. The oh-so-open-close principle suggests that we design our modules to be able to add new functionality in the future, without having to actually make changes to them. Instead, we should extend a module to add to it, be that wrapping it or something else, but we should never modify it directly. Once a module is in use, it's locked, and this now reduces the chances of any new additions breaking your code. Luckily, the luminous Liskov leaves us a lesson that loosely limits how we leverage our legacy code. Okay, that's enough of that. Liskov wants to tell us that we should only extend modules when we're absolutely sure that it's still the same type at heart. For example, we can probably extend a hexagon into a 6-pointed star, because that still makes sense as a 6-sided shape. But we can't really do the same if we wanted a 5 or 7-pointed star, because that would no longer be compatible with what a hexagon represents. It just wouldn't fit cleanly anymore into parts of your code that expect hexagons, and so it will have failed the principle. If that's the case, it should extend something that fits its design or become its own type instead. Almost at the end now, and we have I for interface segregation. It says that our modules shouldn't need to know about functionality that they don't use. We need to split our modules into smaller abstractions, like interfaces, which we can then compose to form an exact set of functionality that the module requires. This becomes especially useful when testing, as it allows us to mock out only the functionality that each module needs. Which brings me to Big D, which stands for dependency inversion. This one is pretty simple to explain because it says that instead of talking to other parts of your code directly, we should always communicate abstractly, typically via the interfaces we define. Dependency inversion breaks down any direct relationships between our code and isolates our modules completely from one another, meaning we can swap out parts as we need to. Because they communicate with interfaces now, they don't need to know what implementation they are getting, only that they take certain inputs and return a valid output. The cool thing about Solid is that when we combine all these principles together, it ends up decoupling our code, giving us modules that are independent of each other and making our code more maintainable, scalable, reusable, and testable. Programming design patterns, not to be confused with principles from the last chapter, are also something I see underused a lot, when they really should have more of a place in your mind. Patterns give us some real solutions to our code problems, but they aren't fixed implementations, so they're still kind of open to interpretation. We use them to architect our software systems, matching the right shapes to fit the needs our software has.
If you've ever opened 20 tabs on Google Scholar trying to figure out what the research says, watch this. Normally, researching a topic means dozens of searches, juggling through a ton of tabs, and spending hours and hours trying to read and screen through papers.
First up, we have creational patterns, which are there to help us make and control new object instances, such as the factory method pattern, which turns a bunch of requirements into different modules that follow the same interface, but aren't necessarily the same type. Then there's structural patterns, which are concerned with how we organize and manipulate our objects, such as the adapter pattern, to wrap a module and adapt its interface to one that another module needs. Finally, there's behavioral patterns, which focus on how code functions and how it handles communication with other parts of the code, such as using the observer pattern to publish and subscribe to a stream of messages in an event-based sort of architecture. Now, there's a bunch of different design patterns under each category. Some of them you might have used before. A lot of these patterns are used by frameworks and by professionals in huge corporations, and that kind of ties in with another pretty unique benefit. The benefit of creating a universal vocabulary of programming. Have you ever written some code that seemed great at the time, but later you had trouble understanding it? Well, it often comes down to the way you name things. Take a look at this snippet. It's quite short, but it's hard to interpret what's going on without some thoughtful analysis. Let's fix this in steps. First up, we should avoid unnecessary encodings, such as type information, which make it harder to read code in a natural way. Next, we have many abbreviations and acronyms that don't really explain well enough what they are. We should expand them to their full names to avoid any miscommunication. Looking better, but it's not really clear what some of these variables hold. They're quite vague and ambiguous. We should aim to use names that more accurately represent the nuances of the code we're working with. We also want to replace magic values, such as the organ index or trigger word string, with named constants. By doing so, we clarify their significance, and we help to keep things in sync if they're used elsewhere. Okay, we can now read this code and understand what it's doing without having to think too hard about it. However, we can still improve it further. If you have any compassion for your future self, or other unfortunate developers who might have to read your code, be descriptive with your names. Ideally, we want to find a balance between being clear enough to quickly understand what the code does, without being so verbose that it becomes an information overload. Remember that no matter how good you think your code is, if it's not easy to read, I would argue that it's not actually good code at all. Many people don't test their code, and that's understandable, I think. Writing tests can be very difficult when code is not properly architected. At the high level, we have end-to-end testing, which lets you test the system as if you were the end user. It's useful because literally any spaghetti code can be end-to-end tested, assuming you can simulate the inputs, as it never actually touches the code itself, only what it delivers to us. They can be tricky to set up though, due to the need to always have a fully functional application running, but they are surprisingly valuable. At the lower level, we have unit tests to verify the operation of our modules in isolation, and integration tests to examine the interaction between those modules. These provide validation that our code is doing what we expect it to, rather than focusing more on behavior, like end-to-end tests. If the thought of writing tests seems overwhelming right now, try applying the solid principles you learned earlier. You might be surprised at how much easier it becomes when your code is modular and decoupled. Number 6 is time, and how you manage it. Time estimation is a process I still fail in sometimes. A common rule of thumb is to double or even triple your initial time estimate for a task. It feels excessive, but it's impossible to predict the unknown problems we will encounter along the way, so we need to account for those. For For example, this video took 3 times as long to make as I had predicted. I really should take my own advice sometimes. Remember that creation goes hand in hand with problems, so in the end, it's better to overestimate and deliver ahead of schedule than it is to miss a deadline. Alright, this one is a bit cheeky, as it's still kind of related to time, but I needed 7, not 6 points to make the Deadly Sins reference, so here we are. All I wanted to say here is that you should try not to rush. Things can feel great when we're blazing through a project, and there's definitely a place for that in prototypes. But remember that if this is going to be a long-term project, take your time and think things through from day one. We'll never get all our decisions right first time, but we can at least give ourselves a better foundation to work from, and hopefully avoid some of that nasty code debt later. Anyway, you're likely to finish in less time regardless if you're not constantly battling decisions you can't easily fix because of poor architecture. We want projects that get easier with time, not harder. And that's it. Wow, you leveled up. Go forth and be the programmer you were always meant to be. I'd like to end with a quote from Martin Fowler. Any fool can write code that a computer can understand. Good programmers write code that humans can understand. Thank you so much for watching. It's been many weeks making this video, but it's all worth it to see that smile of yours now. See you next time.
Let's do this JSON thing. Okay, JSON. Okay. Generalize time. What's JSON is very arrays, traditions, JavaScript object using mechanism of app response.json fetch API. Serialization, deserialization, right? I just need to further contain valid JSON data type. Streamers meaning double quotes, not single quotes. Okay, they said 15 minutes, but clearly it's gonna take a little more than 15 minutes. Alright. Copy raw file. What's that? That's an HTML. Index HTML. Select all. Boom. Okay, this is our superheroes. Okay. Okay. Yeah. Oh. Oopsie. Okay. Has nothing. That's fine. Stringify. Yep. Okay, I guess. Jeez. Okay. I did it out of order. But fine. Why not roll this slow? Cool. It's very cool.